Welcome to this video on TF-IDF, or Term Frequency Inverse Document Frequency. TF-IDF is a key technique used in natural language processing and text analysis. It helps determine the importance of words within a document relative to a collection of documents. By the end of this session, you'll understand how TF-IDF works, why it's useful, and where it is applied. TF-IDF, or Term Frequency Inverse Document Frequency, is a statistical measure used in natural language processing to evaluate the importance of a word within a document relative to a larger collection, or corpus. It works by balancing two factors: term frequency, which counts how often a word appears in a document, and inverse document frequency, which considers how rare the word is across multiple documents. This ensures that commonly used words like is or the are given less importance, while more meaningful terms stand out. TF-IDF is widely used in text analysis, search engines, information retrieval, and text classification to improve the relevance of keywords and enhance document ranking. Why use TF-IDF? First, it helps identify important words by distinguishing relevant terms from common ones. This reduces the influence of frequently used but unimportant words like the or is. Second, it balances frequency and uniqueness. Term frequency identifies words that appear often in a document, while inverse document frequency highlights rare but significant words across multiple documents. Third, TF-IDF enhances search engines, chatbots, and document classification. It improves text analysis by retrieving the most relevant documents from a collection. Finally, it is a simple and effective technique. Unlike deep learning models, TF-IDF is lightweight, easy to compute, and works well for small to medium-sized datasets. Let's first talk about term frequency, or TF. TF measures how often a term appears in a document, helping us determine its importance within that specific document. The formula for TF is the number of times a term appears in a document divided by the total number of words in that document. For example, in the sentence, "NLP is great for text analysis," the word text appears once, while the total number of words in the document is 6. So, the term frequency of text is 1 divided by 6, which equals 0.166. A higher TF score means the word appears more frequently in the document. However, common words like is and the usually have high TF values, which is why we use inverse document frequency, or IDF, to adjust their importance. Let's explore IDF next. Finally, it is a simple and effective technique. Unlike deep learning models, TF-IDF is lightweight, easy to compute, and works well for small to medium-sized datasets. IDF helps us determine how important or unique a word is across multiple documents. It penalizes words that appear frequently in many documents while highlighting rare and meaningful terms. The formula for IDF is the logarithm of the total number of documents divided by the number of documents that contain the word. Let's take an example. Suppose we have a total of 10 documents, and the word text appears in 3 of them. The IDF score is the log of 10 divided by 3, which equals approximately 0.52. This means that common words like the or is will have a lower IDF score, reducing their importance. Meanwhile, rare words like quantum or neural will have a higher IDF score, making them more significant. Now that we understand term frequency and inverse document frequency, let's see how they come together in TF-IDF. TF-IDF is a measure that evaluates how important a word is within a document relative to a larger collection of documents. It does this by multiplying term frequency with inverse document frequency. The formula is simple. TF-IDF equals TF multiplied by IDF. Let's continue with our example using the word text. We previously calculated its TF as 0.166 and its IDF as 0.52. Multiplying these values gives us a TF-IDF score of approximately 0.0863. A higher TF-IDF score means that a word is important in the document, while a lower score indicates that the word appears frequently across multiple documents and carries less significance. This technique is widely used to filter out common words while emphasizing unique and meaningful terms in text analysis. Next, let's apply this concept to a real-world example. The first document says NLP is fun. The second document says text mining is a part of NLP, and the third document says fun with text and NLP. Our goal is to calculate the TF-IDF score for the word text. Step 1. Compute term frequency. In document 1, text does not appear, so its TF is 0. In document 2, text appears once out of 6 words, giving a TF of 1/6. In document 3, text appears once out of 5 words, so its TF is 1/5. Step 2. Compute inverse document frequency. The word text appears in 2 out of 3 documents. Using the IDF formula, we calculate log 3 over 2, which is approximately 0.176. Step 3. Compute TF-IDF. In document 1, since TF is 0, TF-IDF is also 0. In document 2, multiplying 1/6 by 0.176 gives a TF-IDF score of approximately 0.0293. In document 3, multiplying 1/5 by 0.176 gives a slightly higher score of approximately 0.0352. Key insights. The word text is most relevant in document 3 because it has the highest TF-IDF score. It is somewhat relevant in document 2, but completely irrelevant in document 1. This example shows how TF-IDF ranks the importance of words across multiple documents, making it useful for search engines, text classification, and information retrieval. Let's compare TF-IDF with other popular NLP techniques. First, TF-IDF, or term frequency inverse document frequency. This method uses statistical calculations to determine word importance. It is simple, efficient, and easy to implement. However, it ignores word meaning and context. TF-IDF is best suited for search engines, keyword extraction, and document ranking. Next, Word 2 VEC, a word embedding technique. Unlike TF-IDF, Word 2 VEC learns relationships between words based on how they are used in sentences. It captures synonyms and word similarities, making it useful for applications like recommendation systems and sentiment analysis. However, it requires training on large data sets. Finally, BERT, a transformer-based deep learning model. BERT understands context and meaning, allowing it to differentiate between similar words used in different ways. This makes it highly effective for chatbots, machine translation, and question-answering systems. However, it has a high computational cost and requires vast amounts of data. Key takeaway: TF-IDF is a great choice for basic NLP tasks due to its simplicity. However, if deeper insights and contextual understanding are needed, techniques like Word 2 VEC and BERT offer more advanced solutions. TF-IDF offers several key advantages that make it a valuable tool in text analysis. First, it is simple and easy to implement. It relies on basic mathematical formulas and does not require complex machine learning models, making it accessible for many applications. Second, it is efficient for text processing. TF-IDF works well for small to medium-sized data sets, providing quick and lightweight computations compared to deep learning models. Third, it helps identify important words. By highlighting relevant keywords in a document while filtering out common words like the and is, it improves text analysis accuracy. Fourth, it enhances search engine performance. Search engines use TF-IDF to rank web pages more accurately, ensuring users get the most relevant results. Finally, it supports various NLP applications. From information retrieval and text classification to recommender systems, TF-IDF plays a crucial role in multiple domains. A simple yet powerful technique, TF-IDF, continues to be widely used in modern text analysis. Up next, challenges. While TF-IDF is a powerful tool, it does come with some challenges. First, it ignores meaning. TF-IDF treats words as independent units. For example, the words car and automobile are considered completely different, even though they mean the same thing. This lack of semantic understanding can limit its effectiveness. Second, it is sensitive to rare words. If a word appears in very few documents, it receives a high TF-IDF score, even if it's not truly important or relevant. This can sometimes lead to misleading results. Third, it has a high computational cost. For large datasets, calculating TF-IDF requires significant memory and processing power, especially when working with millions of documents. Finally, it lacks context awareness. TF-ID does not consider word order. For example, New York and York New would be treated the same, even though they have different meanings. It also cannot differentiate between phrases where context is crucial. Despite these challenges, TF-IDF remains one of the most widely used techniques in text analysis due to its simplicity and effectiveness. Next, let's explore some real-world applications of TF-IDF. TF-IDF plays a crucial role in various real-world applications. First, in search engines. Platforms like Google and Bing use TF-ID to rank web pages based on keyword relevance, ensuring that the most relevant results appear first. Second, in spam detection. Email filters identify spam messages by detecting uncommon or promotional terms that frequently appear in junk emails but not in regular messages. Third, in text summarization. TF-IDF helps extract key sentences from long documents by prioritizing words with high importance, making it useful for automatic summarization tools. Fourth, in recommender systems. Websites use TF-ID to suggest articles, products, or content based on keyword relevance, improving personalization for users. Even with the rise of advanced models like Word2Vec and BERT, TF-IDF remains widely used because of its simplicity and efficiency. Next, let's wrap up with our final thoughts on TF-IDF. To conclude, let's go over the key takeaways. TF-IDF is a powerful technique for identifying important words in a document compared to a collection of documents. It effectively balances term frequency and inverse document frequency to rank word importance. Despite its limitations, TF-IDF remains a widely used approach in various applications, including search engines, spam filters, and text classification systems. While advanced models like Word2Vec and BERT offer deeper context understanding, TF-IDF continues to be a simple, efficient, and effective tool for text analysis. Thank you for your time.